There is a moment just before the world falls asleep when the noise of our lives seems to dissolve. The hum of machines fades. The traffic thins. The light outside the window softens into a quiet blue. If you listen closely in that moment, you might feel something subtle moving beneath the surface of the world. Something vast. Something old. A rhythm that does not belong to any creature, any civilization, or any age we know. It is the rhythm of the planet itself. For as long as humans have existed, we have been trying to understand that rhythm. We study the clouds, the seasons, the storms. We carve calendars in stone. We build clocks to tame time. But for all our tools, for all our models and measurements, there has always been one question the Earth has never really answered. Why does the warmth of our world not last? It is easy to imagine that the climate we see today is the natural state of Earth. We look at forests and oceans and fields of grain and assume these are permanent features. We picture the poles capped in ice and imagine those icy crowns have always been there and always will be. We mistake what is familiar for what is normal. But the Earth we know, the green Earth, the stable Earth, exists only because we are living in a brief, improbable pause. A narrow window in a much larger cycle that we have only recently begun to understand. Every 100,000 years, the planet changes its mind. It pulls warmth away from the continents. It grows white and silent. It becomes a world of ice. And then just as suddenly the ice collapses, the oceans rise, and the warmth returns. This happens not once, not twice, but over and over again, with the precision of a heartbeat. We have a name for this rhythm now. We call it the Ice Age cycle. But behind that simple phrase is a mystery so large it stretches from the core of the Earth to the edge of the solar system. If the planet has a heartbeat, then what exactly is the heart listening to? To begin this journey, we must confront a deeply uncomfortable truth. The climate that supports our cities, our food, our history, even our dreams is not the default setting of Earth. It is the anomaly. We evolved during chaos, but we built our world during calm. And that calm should, by all the rules of nature, have ended long ago. Before we go any further, take a moment to tell me in the comments where you are listening from and what time it is for you right now. I am always amazed by how far these stories travel, and how people across the world join this journey together. And as always, the images you see here are only meant to set the mood. They are not required to imagine these mysteries. And since a new year is approaching, I want to send you a quiet wish from here. May the next chapter of your life arrive with the same sense of wonder that brings you to these stories. Thank you for being here and for walking into these forgotten rhythms with us. According to the cycles written in ice and stone, and in the quiet math of the sky, the next ice age should already be approaching. The summers should be weakening. The snow in the far north should be refusing to melt. Glaciers should be stirring in the mountains of Canada and Scandinavia, preparing for a slow march south. And yet none of that is happening. The world is warm. Warmer than it should be. Warmer than any interglacial period that came before. Something is holding the ice at bay, something powerful enough to override the rhythm that has governed this planet for more than 1 million years. Tonight we will follow that rhythm from its smallest signs to its grandest forces. We will travel deep into the Antarctic ice, where ancient air has been trapped for nearly 1 million years. We will follow a Serbian mathematician sitting in a prison cell who discovered the celestial gears that push and pull our climate. We will stand on the mammoth steppe that once stretched across half the world. We will listen to the breath of the planet as it moves from cold to warmth and back again. And as we move through the long sweep of time, a larger question will begin to rise. If the ice ages always return, why did they stop for us? What force was strong enough to break a 1 million-year cycle? And what will happen when that force begins to fade? For now, hold this question in your mind. Imagine the Earth not as a rock circling the sun, but as a living body with a long, slow pulse. Imagine that pulse happening once every 100,000 years. Imagine that every time the Earth inhales, the continents freeze beneath 3 kilometers of ice. And imagine that every time it exhales, the oceans rise and forests return and life begins again. We are living in the exhale, in the long, warm breath that made civilization possible. But breaths are not infinite. They end. And if we want to understand our future, we must first understand this pulse, this cycle, this million-year pattern that has shaped not only landscapes, but the destiny of every creature on Earth. So let us begin with the question the planet never answered. Why do the ice ages return every 100,000 years? And why did we stop the next one before it began? That is the story waiting in the dark beneath the ice and in the silent mathematics of the heavens. That is the mystery that will unfold from this moment forward. If you step outside on a warm evening and feel the air settle gently on your skin, it is easy to believe that this is the natural state of the Earth. A comfortable planet, mild and predictable, wrapped in green landscapes and blue oceans. A place where seasons follow one another with familiar precision. A place where warmth seems permanent. But this sense of stability is an illusion. It comes from the narrowness of our experience. A human lifetime is a short flicker against the backdrop of geological time. Civilizations rise and fall in minutes compared to the slow breathing of the planet. Even our oldest stories can only reach back a few thousand years. We have never seen the Earth as it truly is. We have only seen it during one of its rare moments of calm. To understand this illusion, imagine compressing the entire history of Homo sapiens into a single long timeline. On that timeline, the world we know today, the stable climate of the Holocene, occupies only the final sliver, a thin and delicate thread that barely clings to the edge. Everything before it looks different, almost unrecognizable. For most of human existence, the Earth was not warm, it was white. Not white like snow on a winter morning or frost on a car window. Not a thin seasonal dusting, but white on a planetary scale. A world covered in ice thousands of meters thick. A world where the wind carried knives of cold and the oceans retreated far beyond distant horizons. A world where the land we now inhabit did not exist at all. During the height of the last ice age, if you stood on the coastline of modern Europe, the sea would not have been at your feet. It would have been a distant memory on the horizon. The English Channel did not exist. Britain was not an island. It rose as a range of hills above a vast plain called Doggerland, a windy grassland stretching from what is now the Netherlands to the cliffs of Dover. Mammoths grazed where the North Sea now churns. Rivers the size of great modern waterways flowed across land that today lies buried under waves. In North America, the transformation was even more dramatic. A continent-sized wall of ice rose over what is now Canada and the northern United States. At its center above the region we call Hudson Bay, the ice towered higher than the Rocky Mountains. If you stood at its base, you would be looking up into the edge of the sky. The weight of this sheet was so immense that it bent the crust of the earth downward like a heavy hand pressing on a floating raft. This was not a frozen wasteland of endless storms. It was something colder and more silent. The air was so dry that very little snow actually fell. Winters were not defined by storms but by the absence of heat. The cold was not just a temperature, it was an atmosphere, a condition that shaped everything. We think of deserts as hot places, but during the Ice Age, the largest desert in the world stretched across Eurasia, from Spain to Siberia. It was called the Mammoth Steppe, a cold, dry grassland supporting herds of giant animals. Here humans moved through tall, wind-blown grasses following mammoths, bison and horses across a continent that no longer exists. This world is alien to us. It feels like a different planet, and yet it was Earth for nearly all of the last 1,000,000 years. When we look around at the climate of today, we see stability. We see forests that do not shift their boundaries by hundreds of miles every few centuries. We see coastlines that stay where they are for the span of countless human generations. We see rains that fall on seasonal schedules, predictable enough to plant crops and build cities. This stability is the foundation of our civilization. But it is not the nature of the Earth. It is the exception. The planet has always been governed by a much older rule, a cycle that brings warm periods like ours only briefly and sends them away just as quickly. The Holocene. The warm epoch we live in has lasted just over 11,000 years, long enough to invent agriculture, long enough to build empires, long enough to leave our mark on the land. But compared to the long epochs of ice before it, the Holocene is little more than an intermission, a pause between acts in a much larger story. If we had been born 10,000 years earlier, we would have lived in a world of frozen horizons. If we had been born 10,000 years later, we likely would have witnessed the first signs of the next ice advancing from the north. Our cities would never have existed. Our crops would never have taken root. Our history would never have begun. And yet here we are suspended in this narrow moment, a moment that by all the patterns of the past should have already ended. Earth should be cooling now. The long decline into the next ice age should be underway. The forests of the far north should be retreating. Glaciers in the Scandinavian mountains and the Canadian Arctic should be growing thicker each winter, surviving each summer, climbing slowly down valleys carved by their ancient ancestors. But they are not. Instead, the world is warmer than expected. The seasons are not weakening. The ice is not returning. Something has interrupted a cycle that has repeated with relentless discipline for hundreds of thousands of years. This is the illusion of stability. It is not that the world is naturally calm. It is that the chaos of the ice ages has been paused by something unexpected, something powerful enough to silence the rhythm that shaped every glacial cycle before us. The evidence is not in the world we know. It lies far below it, in a place where the past is still intact. It is buried in a frozen archive on the edge of the planet. The frozen archive lies in the interior of Antarctica, a place so silent and so hostile that almost nothing endures there except time itself. Snow does not melt. Winds sculpt the same ridges for centuries. And deep below the surface, layer upon layer, the planet has recorded its own past with perfect precision. Not the Antarctica of maps and textbooks, not the white shape at the bottom of the globe. This is the interior, the high plateau, a desert of ice so vast and so featureless that it blurs the boundary between earth and sky. Here winter never truly ends. The cold is so deep that breath freezes the instant it leaves the lungs. The horizon stretches in every direction without a single tree, rock, or shadow to break its emptiness. In this place stands an outpost called Vostok. There is nothing romantic about Vostok. No dramatic peaks, no crashing waves, no wildlife passing in silence. Only a scattering of structures half buried in snow, a few antennae pointing into a wind that never stops, and a cluster of generators humming against the cold. It is one of the most isolated research stations on Earth. Yet beneath the boots of the scientists who work here lies a treasure more valuable than gold or oil or ancient ruins. It is a record, a library, a perfectly preserved archive of Earth's climate stretching back almost 1,000,000 years. This archive is made of ice. Snow that falls on the Antarctic plateau does not melt. The temperatures are too cold even in summer for liquid water to exist. Instead, each year's snowfall remains where it lands, layer after layer, century after century, millennium after millennium. The weight of new snow presses down on the old snow, compacting it, crushing the air between its crystals, and eventually transforming it into clear blue ice. This process traps something extraordinary. Inside that ice are tiny bubbles, microscopic spheres of air sealed off the moment the snow was compressed. These bubbles are not symbolic or poetic. They are literal pieces of past atmospheres frozen in place. When scientists drill down through the ice and extract long cylinders known as ice cores, they are holding in their hands the air that ancient humans and ancient animals once breathed. If you drill down 100 meters, you find air from the time of the Roman Empire. If you drill down 1,000 meters, you reach air older than agriculture, older than writing, older than civilization. But at Vostok, the ice is nearly 4,000 meters thick. At that depth, the bubbles come from a world with no cities, no humans, no human ancestors recognizable to us today. A world of ancient winds and unbroken wilderness. Extracting this air is delicate work. In the laboratories where the cores are studied, scientists cut small sections of the ice and place them inside vacuum chambers. As the ice melts or shatters under controlled pressure, the ancient air is released. Instruments measure its composition: the carbon dioxide, the methane, the dust, the isotopes of oxygen and hydrogen. Each measurement reveals something about the temperature of the world at the moment that layer of snow fell. By stacking these layers one on top of another, year after year, the scientists built a timeline, a vertical history of the climate. When they plotted the results on a graph temperature on one axis and time on the other, they expected to see some irregularity, some slow drift punctuated by random fluctuations. Climate, after all, is complicated, but that is not what they saw. The graph did not wander. It did not drift in gentle slopes or chaotic leaps. Instead, it formed a repeating serrated shape, like the teeth of a saw. Long, gradual declines into deep cold followed by sudden, dramatic spikes into warmth. Down slowly for 90,000 years. Up sharply for 10,000. Down again. Up again. Over and over. This was not chaos. This was structure, precision, a pattern repeating 8 times across the last 800,000 years. A heartbeat. The scientists knew what they were looking at, even if the implications were unsettling. Each long descent represented the growth of the ice sheets. Each steep rise represented their collapse. Each cycle took roughly 100,000 years, almost as if some vast mechanism was pushing and pulling the entire planet in and out of glacial states. The question was not whether the cycle existed. The data was too clear for doubt. The question was, what force could possibly impose such regularity on a world full of volcanoes, oceans, storms, continents, and life? Earth is a chaotic planet. Weather changes by the hour, climate changes by the millennium, but nothing on Earth operates on a perfectly repeating 100,000-year schedule. No volcano erupts like a clock. No ocean current resets itself like a heartbeat. No mountain range rises or falls in rhythm. So where was this rhythm coming from? In the quiet of the Antarctic laboratories, as scientists compared core after core, the same thought surfaced again and again. The signal was too strong, too precise, too ancient. It could not be coming from Earth at all. This was the first hint that the true engine behind the ice ages was not buried in the planet, but far above it. Somewhere in the silent vastness of space, something was nudging the Earth, in a way subtle enough to be invisible, but powerful enough to freeze continents on schedule. At the time, this idea was only a whisper in the data, a possibility, a question waiting for a mind willing to chase it. That mind would not be found on the frozen plains of Antarctica. It would be found in a prison cell thousands of miles away, where a man armed with nothing more than a pencil and a stack of paper would uncover the hidden clockwork of the solar system. Before we meet him, we must understand what his discovery truly meant. The ice beneath Antarctica recorded not just the climate of the past, but the future we should already be experiencing. It showed that the cold should be returning, that the planet should be sliding back into another glacial era. But it is not. And the reason why is a revelation still unfolding in our own time. When the first complete climate record from Antarctica was revealed, many expected complexity. They expected tangled lines and irregular shifts. They expected evidence of a climate that wandered, drifted, or lurched unpredictably through deep time. What they did not expect was a heartbeat. It is one of the most striking images in all of climate science. A graph stretching almost 1,000,000 years into the past, rising and falling with a rhythm so regular it looks less like the history of a planet and more like the readout of a machine. Long, slow descents into deep cold, followed by sudden sharp spikes of heat, like the breath of something sleeping, like the pulse of something alive. Down for 90,000 years, up for 10,000, down again, up again, relentless, precise, repeating. The more scientists stared at this pattern, the more astonishing it became. The Earth was not drifting randomly between warm and cold. It was following a rule, a schedule, a cycle that had repeated 8 times across the last 800,000 years. Each cycle lasted roughly 100,000 years. And because the last warming spike occurred 11,700 years ago, the beginning of the Holocene, we are now living in the tail end of the most recent pulse. According to the pattern, the warmth should be fading. The long decline into the next ice age should already be underway. But before we jump ahead to what this means for our future, we must understand the cycle itself. Because the sawtooth pattern recorded in the ice is not just a graph. It is the blueprint for how Earth resets itself. A story of collapse and rebirth repeated again and again across geological time. The descent into an ice age is slow. Too slow for any civilization to notice. Too slow for any species to truly comprehend. Temperatures fall by tiny fractions over centuries. Snow in the far north lingers a little longer each summer. Glaciers extend their reach by a few kilometers. The forests retreat. The winds grow sharper. What begins as a subtle shift becomes a creeping transformation that redefines entire continents. But the end of an ice age is something else entirely. The warming spike, the vertical rise in the sawtooth is fast, violent, dramatic. It represents a sudden release of energy on a global scale, a collapse of ice sheets thousands of meters thick, a surge of meltwater that can raise sea levels by tens of meters in a single geological instant. Compared to the slow march into cold, the return to warmth is an explosion. This asymmetry, the slow freeze and the fast thaw, is one of the most defining signatures of the Ice Age cycle. It is what gives the graph its shape. Long teeth pointing downward into cold, and sharp blades slicing upward into heat. The cause of this asymmetry is part of a larger mystery, one that scientists would wrestle with for decades. Why is the freezing slow and the melting fast? Why do the ice sheets grow patiently but collapse catastrophically? Why does the planet cool like a drifting feather but warm like a snapped rope? These questions would eventually lead to the discovery of powerful feedback loops that amplify small changes. But those feedbacks alone cannot explain why the entire planet freezes and thaws on a clock-like century scale, repeating with such stubborn precision. Something else must be setting the tempo. Something must be keeping the rhythm. This is where the heartbeat metaphor becomes more than a poetic comparison. In physiology, a heartbeat is created by an external driver, a signal that pulses repeatedly and forces the body to respond. Without that signal, the rhythm collapses. Climate scientists realize the same must be true for the Ice Age cycle. The Earth cannot generate a 100,000-year rhythm from chaos. Nothing in the oceans or the atmosphere operates on such a timescale. Nothing on Earth is precise enough to carve this pattern into 1,000,000 years of climate history. So what then is striking the drum? There is a moment in the Antarctic labs where this question becomes more than academic. A researcher holds an ice core under the sterile lights of the facility, a cylinder of ancient compressed snow. The air inside it is older than cities, older than human language, older than the idea of history itself. He knows that the bubbles trapped in this ice come from a world colder than anything modern humans have seen. He knows that the pattern encoded in these bubbles, the rise and fall of temperatures over hundreds of thousands of years, was not an accident. And in that silence, staring at the repeating cycle, the idea finally becomes unavoidable. This rhythm is not Earth's doing. It is coming from beyond, something outside the climate system, something larger, steadier, and more patient than the Earth itself, is nudging the planet into this cycle. Something in the way the Earth moves through space, something in the geometry of orbit and tilt and distance. The heartbeat in the ice is a shadow cast by celestial mechanics. But this realization only deepened the mystery, because if the cycle is written in the motions of the planet through the solar system, then the Earth should be responding to it right now. The next cooling phase should have begun thousands of years ago, which leads to an even more unsettling conclusion. The rhythm is still there. It has not vanished. The clock is still ticking. The celestial gears are still turning exactly as they always have. But Earth is no longer listening. For hundreds of thousands of years, the planet responded to this signal without fail. And then suddenly, during the brief moment when humans arrived, built cities, and began to alter the atmosphere, the cycle stopped. Why did this happen? And what exactly changed? If you were searching for the person who unraveled the deepest climate mystery on Earth, you might imagine an explorer standing on the Antarctic ice, or an astronomer looking through a powerful telescope, or perhaps a physicist surrounded by machines and equations. What you would not imagine is a prisoner. Yet that is where the answer began. The year was 1914. Europe was descending into the chaos of the First World War. Armies mobilized, borders collapsed. The world began to fracture under the pressure of alliances and ambition. And in the middle of this rising storm, a Serbian engineer and mathematician named Milankovitch was arrested by the Austro-Hungarian authorities. He had committed no crime. He was simply on the wrong side of a political divide at the wrong moment in history. He was taken from his honeymoon, separated from his wife, and confined first in a camp and then in a small room in Budapest, where he waited to learn his fate. Outside his window, the world was tearing itself apart. Gunfire echoed across Europe. Nations that had existed for centuries were collapsing in real time. Inside the room there was silence. The story could have ended there, another life interrupted by war. But Milankovitch was given a small mercy. He was allowed access to the library of the Hungarian Academy of Sciences, where he spent his days surrounded by books and the dim glow of candles. And in that strange sanctuary, while the world outside fought over borders, he turned his attention to something far grander, something that ignored borders entirely, something that had been unfolding long before humanity and would continue long after war and civilization and memory were gone. He chose to calculate the climate of Earth for the past 600,000 years. This was not the ambition of a man working in a peaceful observatory with instruments and data. Milankovitch had no computers, no satellites, no ice core records, no modern measurements. What he did have were the laws of physics, a slide rule, and a mind capable of imagining the Earth not as a static world, but as a moving piece of celestial machinery. He reasoned that if the climate was changing on a schedule, then that schedule must be tied to something outside the climate system, something stable, something mathematical, something predictable enough to impose order on chaos, that something he believed was the sun. To Milankovitch, the Earth was not warmed by volcanoes or oceans or atmospheric currents. Those things responded to heat. They did not create it. All of the energy that drives wind, rain, storms, and seasons comes from one place, the star at the center of the solar system. So if the Earth alternated between warm periods and ice ages, the cause must be found not in the planet itself, but in the way the planet moved through the light of the sun. He began with the simplest idea. If the amount of sunlight reaching the Earth changed over long timescales, then the climate would change as well. But the total amount of sunlight reaching Earth does not vary very much. The sun does not flicker like a candle. It burns with remarkable consistency. So the key could not be the total amount of sunlight. It had to be the way that sunlight fell, where it fell, when it fell, how intense it was in the places that mattered most for the formation of ice. This idea seems obvious now, after a century of scientific progress. But in Milankovitch's time it was revolutionary. The dominant belief was that climate was controlled entirely by earthbound forces, volcanic eruptions, atmospheric composition, ocean currents, perhaps even continental drift. The heavens were thought to be irrelevant. Milankovitch disagreed. He understood that the Earth does not follow a simple path around the Sun. It wobbles, it tilts, it stretches. It traces an orbit whose shape is constantly being tugged by the gravitational pull of the giant planets Jupiter and Saturn. These movements are so slow that no human being would notice them in a lifetime. But given enough time, those small nudges accumulate. They shift the angle of the planet. They change the timing of the seasons. They alter the amount of summer sunlight falling on the northern hemisphere, which is the true trigger for the survival or disappearance of snow. Milankovitch spent years filling notebook after notebook with calculations, sketching out the geometry of Earth's orbit through deep time. He tracked the tilt of the axis, the wobble of the poles, and the stretching of the orbit over hundreds of thousands of years. He built a mathematical model of how much sunlight reached different latitudes at different points in Earth's history. The conditions inside his room never changed. The war raged. The world outside remained uncertain and dangerous. But inside those pages something extraordinary began to appear. A pattern. When he plotted the amount of summer sunlight falling on the northern hemisphere against time, he saw rhythmic variations. Subtle shifts that repeated over tens of thousands of years. These shifts matched almost exactly the known timing of glacial and interglacial periods. He saw that the orbit stretched on a 100,000-year cycle, that the tilt of the axis changed on a 41,000-year cycle, that the wobble of the Earth's rotation traced a 23,000-year cycle. 3 rhythms, 3 gears, each turning slowly but predictably. And when those gears aligned, they produced exactly the conditions needed to cool the northern summers so much that winter snow could survive and build the great ice sheets. He had found the heartbeat. A century later, scientists working with ice cores would confirm his predictions with astonishing accuracy. They would discover that the climate changed in perfect harmony with the celestial cycles Milankovitch described from a prison cell. His theories would become the foundation for modern paleoclimatology. But the most astonishing part of the story is not the math, it is the timing. Milankovitch showed that the cooling phase leading to a new ice age should begin when the key drivers, the tilt, the wobble, and the orbit, align in a particular configuration. According to his calculations, that alignment happened several thousand years ago. By his model, we should already be cooling. By the pattern in the ice, we should be sliding toward cold. Yet we are not. The cosmic clock has struck its hour, and the Earth has not answered. Something has broken the link between the celestial signal and the planetary response. Something has overridden the heartbeat. The explanation begins with the slow celestial rhythms Milankovitch uncovered. 3 great cycles operating in silence set the tempo of every ice age. Within them, the pattern finally becomes clear. The first force shaping the rhythm of the ice ages is distance itself. Earth does not travel around the Sun in a perfect circle. It drifts closer and farther in a long, slow cycle that unfolds too gradually for any human lifetime to notice. But from a higher vantage point, far above the orbit of satellites and the haze of the atmosphere, the pattern becomes unmistakable. The planet traces an ellipse, a path stretched gently at the sides, like a ring pulled into an oval. This subtle change in shape is called eccentricity, and though it unfolds over 100,000 years, its influence is immense. When the orbit is more circular, Earth receives sunlight more evenly throughout the year, but when the orbit stretches into its elongated form, one side of the journey carries the planet deeper into the cold. It is here, in this slow breathing in and out of distance, that the Ice Age cycle begins its long descent. We tend to imagine orbits as fixed things. The Earth goes around the Sun, the Moon goes around the Earth. The planets stay in their tracks like trains on rails. But in reality, the solar system is a crowded landscape of gravitational influences. The giant planets Jupiter and Saturn are not passive neighbours. They tug at the Earth constantly. Each time our planet swings past them, it feels a faint pull, far too subtle to matter in a single year, but powerful when accumulated over tens of thousands of years. Under this continual pressure, Earth's orbit stretches and relaxes in a great slow cycle that takes about 100,000 years to complete. Sometimes the orbit is nearly circular, keeping Earth at a relatively steady distance from the Sun throughout the year. At other times, the orbit is more elongated, with one side pulling far out into deeper, colder space. This change does not seem dramatic. In the stretched phase, the Earth is only a few million miles farther from the Sun at its most distant point than it is today. On the scale of the solar system, that distance is small. On the scale of a planet's climate, it is enormous. To see why, imagine standing near a campfire. A small step back does not extinguish the heat, but it weakens it enough that your body notices. Your skin cools first, then your breath, then the ground beneath your feet. Now imagine taking that step back not for a moment but for thousands of years. Imagine the Northern Hemisphere receiving slightly less summer heat every year for millennia. Imagine the snow that falls each winter melting just a little less each summer. This is the quiet power of eccentricity. It does not freeze the world on its own. It simply tilts the planet toward a cooler state by adjusting how far we travel from the Sun. And over long enough time, those subtle differences accumulate until the balance of melting and freezing shifts. When the orbit is elongated, Earth spends more time at the far cold end of its journey. Winters lengthen, summers weaken, snow accumulates, glaciers grow, and once they begin to grow, other forces take over forces that amplify the cold and help transform a slight orbital shift into a full ice age. But the role of eccentricity is more than just distance, it is timing. The elongated orbit means that the difference between the Sun's closest point and its farthest point becomes significant. If this happens to align with the orientation of the Earth's tilt and wobble, summers in the north can become exceptionally weak. If alignment happens the other way, summers become stronger. Eccentricity sets the stage on which the other cycles perform. In the circular phase of the orbit, winters and summers remain more balanced. The amount of energy the northern hemisphere receives from the Sun stays relatively constant. If the tilt and wobble shift toward a cooling configuration during this time, their influence is weaker. The Earth stays warmer. Ice sheets struggle to form. But in the stretched phase, the stakes change. Now the planet is vulnerable. A small decrease in summer sunlight can have outsized effects. Snow that might have melted in a circular orbit now survives. Surviving snow becomes accumulating ice. Accumulating ice becomes a growing ice sheet, and a growing ice sheet becomes a reflective mirror that cools the planet further. This is why eccentricity is the primary rhythm of the ice ages. It determines when the Earth is sensitive to cooling and when it is resistant. It sets up the conditions that allow the other cycles to act with power. Scientists studying the ice cores at Vostok were stunned to see how precisely the 100,000-year cycle of eccentricity matched the rise and fall of the ice ages. The timing was almost perfect. Every major glacial expansion in the last million years aligned with a period when the Earth's orbit was stretched into its most elongated shape. This was the first piece of evidence that the heartbeat recorded in the ice was not an accident. It was tied directly to the geometry of the solar system. It was written not just in snow and ice, but in the movement of planets through space. But eccentricity alone does not cause the ice ages. If it did, every elongated orbit would create glaciers, and every circular orbit would melt them. Yet the climate record shows something more complex. Some elongated periods do not trigger full glaciations. Some circular periods do not produce complete melting. The orbit sets the tempo, but the Earth still needs a conductor. That conductor is sunlight specifically, the way sunlight falls on the northern hemisphere during the summer. That is where the second and third gears come in. The tilt of the Earth determines how much sunlight reaches the far north. The wobble of the axis determines when that sunlight arrives. Together, these two cycles control the intensity of northern summers. But it is eccentricity that amplifies or weakens their influence. When the orbit is stretched, the tilt and wobble have the power to tip the world into deep cold. When the orbit is circular, they do not. The more Milankovitch calculated, the more he realized that eccentricity was the slow drum beating beneath the other rhythms, the one that created the framework, the one that made the sawtooth pattern possible, the one that forced the planet to breathe slowly, inhaling ice and exhaling warmth on a 100,000-year schedule. And yet there is a deeper mystery. The variations in sunlight caused by eccentricity are small, far too small to freeze a planet by themselves. The difference in energy is not enough to explain walls of ice 3 kilometers tall. The orbit is the trigger, but something on Earth is the weapon. That weapon is connected to the tilt of the axis. The second gear is tilt, and it decides how fiercely the sun strikes the northern summer. If eccentricity sets the slow rhythm of the ice ages, then the second gear determines their strength. It is a quiet movement, subtle but decisive. A shift so small it is almost invisible, yet powerful enough to decide the fate of continents. It is the tilt of the Earth. We learn about the tilt when we are very young, 23.5 degrees, a simple number that explains the seasons. When the northern hemisphere tilts toward the sun, we have summer. When it tilts away, winter arrives. The geometry feels straightforward, almost elegant. But this angle is not fixed. It moves. Slowly, over a cycle that lasts about 41,000 years, the Earth rocks back and forth like a spinning top under a gentle hand. Sometimes the axis tilts more deeply, up to 24.5 degrees. At other times it straightens slightly to just over 22 degrees. A 2-degree difference. Insignificant on paper. Transformative in reality. To understand why, imagine standing at a high latitude in the far north. Picture yourself on a tundra that stretches to the horizon in every direction. Now imagine the sun rising in June at a shallow angle, gliding low across the sky, not as a fierce summer star, but as a distant light diluted by atmosphere. It shines for many hours, yet somehow it never feels hot enough to break the cold. This is a low-tilt summer, and this is the paradox at the heart of the ice ages. Ice does not form because winters are cold. Winters are always cold in high latitudes. Ice forms because summers are weak. If the summer sun is too low, too soft, too diluted to melt the snow left behind by winter, that snow survives. One surviving layer becomes the seed of the next. Year after year it piles upward, first as snow, then as compacted granular crystals, and finally as dense blue ice. What began as a single unmelted patch becomes a glacier. What began as a glacier becomes an ice sheet. And once a continent is covered in white, the planet begins to cool itself with mirrors. The tilt is the gatekeeper of this entire sequence. When the tilt is high 24.5 degrees, the sun climbs higher in the northern sky during summer. Its rays strike with more intensity. Snow melts quickly. Ice struggles to survive. Even if eccentricity reduces the sun's energy slightly, a high tilt summer is strong enough to wipe the slate clean each year. But when the tilt is low, everything changes. The summer weakens just enough that the snow does not disappear. It lingers on rocks and ridges. It persists on mountain slopes. It remains as a thin shining layer across northern plains. And because it is white, it reflects sunlight. Because it reflects sunlight, it cools the air above it. Because the air cools, the next winter arrives a little sooner. And when that winter's snow falls, it lands on top of a foundation that nature failed to erase. This is how ice grows. It grows not from storms or blizzards or sudden freezes. It grows from an accumulation of small failures, small summers not strong enough to do their job. That is the quiet power of obliquity. Milankovitch understood this in a way few had before him. He calculated how the tilt altered the distribution of sunlight across latitudes, and how these subtle shifts determined whether the northern hemisphere experienced strong or weak summers. He saw that during periods of low tilt, the intensity of northern summer sunlight dropped just enough to allow snow to persist. This effect is strongest in the northern hemisphere because it contains more land at high latitudes than the southern hemisphere. Land can store snow. Oceans cannot. Snow falling on land accumulates. Snow falling on ocean melts. So the ice sheets of the ice ages are a northern story controlled by northern summers shaped by the tilt. But one question remained. If the tilt can weaken summers enough to begin building ice sheets, why does it not always create ice ages? The tilt follows a predictable 41,000-year cycle. Should that not produce frequent regular glaciations? The answer lies in the interplay between tilt and eccentricity. When the orbit is circular, the effect of tilt is muted. A low tilt summer may be weak, but not weak enough to overcome the stability provided by a consistent Earth-Sun distance. Snow may linger, but it does not accumulate fast enough to sustain growth across centuries. But when the orbit is elongated, and the Earth is pushed farther from the Sun during northern summer, a low tilt becomes dramatically more powerful. Now the summer is not only low in angle, but low in intensity. The Sun is both dimmer and lower in the sky. It is a double weakening, and in that rare alignment, the seeds of an ice age take root. This is why the tilt is the second gear. It does not set the tempo. It determines when the tempo matters. It decides whether the slow pull of eccentricity results in slight cooling or a full planetary transformation. To visualize this, imagine the Earth slowly straightening its posture, reducing its tilt degree by degree across thousands of years. Imagine the sun's arc in the sky flattening, its rays growing weaker at the shoulders of the world. Imagine snow lingering where it once melted, rivers freezing earlier, glaciers beginning to push outward, carving valleys and sharpening peaks. Nothing dramatic happens in any single year. No sudden shift marks the transition. Yet somewhere on a mountain in northern Canada, a patch of snow that should have vanished in July remains until September. The next year it remains until October. The next year until November. And within a few lifetimes, a small ice patch becomes a permanent mass. Civilizations rise and fall too quickly to see this. Humans watch the weather, not the seasons of millennia. But the Earth watches everything. And when the tilt falls into its low phase, the planet enters a period of vulnerability. For most of the last million years, low tilt has been the opening note of an ice age. But something about the current low tilt period is different. According to orbital mechanics, the tilt has been decreasing for thousands of years. We should be cooling. Ice sheets should be growing. But they are not. The tilt is doing what it has always done. The orbit is doing what it has always done. The wobble is shifting exactly on schedule, yet the snow melts, the ice retreats, the summers remain strong. Something has interrupted the second gear. Something has strengthened summer beyond the reach of geometry. Something has changed the rules. Now the cycle shifts to the third gear, the one that determines not how much sunlight reaches us, but when it arrives. This third gear is called precession. Imagine a spinning top. When it spins fast, it stands upright. When it begins to slow, the top starts to wobble. The wobble does not topple the top immediately. Instead, the axis of the top slowly traces a circle in the air. The Earth behaves the same way. Our planet spins like a giant top, but its axis is not fixed. It wobbles slowly, completing a full circle every 23,000 years. Today, the North Pole points toward a star called Polaris. 12,000 years ago, it pointed toward a different star, Vega. 12,000 years from now, it will point back toward Vega again. These changes in the direction of Earth's axis may seem irrelevant. After all, what does it matter which star our planet points toward? But the wobble determines something far more important than the identity of the North Star. It determines when seasons occur in Earth's orbit. Because the Earth's orbit is not a perfect circle, there are times when the planet is closer to the Sun and times when it is farther. Right now, Earth reaches its closest point to the Sun in early January, during northern winter. It reaches its farthest point in early July, during northern summer. This arrangement gives the northern hemisphere slightly milder winters and slightly cooler summers. But precession slowly shifts this schedule. In another 12,000 years, the northern hemisphere will experience winter at the farthest point of Earth's orbit, when the Sun is dimmest in the sky. Summers will occur when Earth is closest to the Sun. The seasons will flip in intensity. This change does not alter the total energy Earth receives from the Sun each year, but it dramatically alters when that energy arrives. And the timing of sunlight is crucial, because summers are the key to the survival or destruction of snow. To understand the significance of this, picture two worlds. In the first world, northern summer happens when Earth is close to the Sun. The Sun climbs higher. The sunlight is stronger. The snow melts quickly. Ice has no chance to accumulate. In the second world, northern summer happens when Earth is at its farthest point from the Sun. The Sun is dimmer, weak, lower in the sky. Snow melts slowly or not at all. A low tilt combined with a distant summer becomes a dangerous combination. A seed of ice survives. One seed becomes many, and the cycle of glaciation begins. Precession is the mechanism that decides whether summer reinforces warmth or becomes a fragile season unable to erase the winter. When Milankovitch first calculated the effect of precession, he realized something startling. The wobble dramatically amplifies or weakens the other two cycles. It does not act alone. It works in concert with the tilt and the shape of the orbit. When all three cycles line up in a cooling configuration, low tilt, elongated orbit, northern summer at the farthest point from the Sun, the ice responds immediately. Summers become too weak to melt the snow of the previous winter. A runaway process begins. But when precession aligns summers with the close point of the orbit, even a low tilt may not be enough to let ice survive. The wobble is the fine-tuner of the planetary rhythm. Small changes in timing make massive differences over time. A shift of a few days in the arrival of summer sunlight may seem trivial, but on a planet with vast frozen landscapes that operate on thousand-year scales, those days matter. They accumulate. They build into trends that shape the destiny of continents. To visualize this effect, imagine the Earth in slow motion, rotating through seasons marked not by months, but by millennia. Each wobble of the axis nudges the calendar, not by days or months, but by entire epochs. What is a minor shift for a human lifetime becomes monumental for the life of a planet. As scientists continue to study Milankovitch's work, they began to see patterns they had not noticed before. Every major glacial period in the last million years began when precession placed northern summer at the far end of the orbit. Every major melting event occurred when precession placed northern summer at the near end. The tilt made summers weaker. Eccentricity made distance matter. But precession decided when that distance would hit hardest. It is the conductor that tells the other gears when to act. What makes precession so extraordinary is how closely its cycle matches key climate transitions in the ice core record. When plotted over hundreds of thousands of years, the wobble shows peaks and troughs that align with the rise and fall of ice sheets. It does not determine the length of the ice age, but it does determine the timing of its beginning and its end. And here lies the most important detail of all. Right now, at this very moment in Earth's history, precession is moving the northern hemisphere toward a cooling configuration. The tilt is decreasing. The orbit is slowly shifting toward greater eccentricity. Northern summer is gradually moving away from the sun. The celestial gears are aligning. By the rules of the past, this should be the beginning of the next glacial cycle. The snow in the far north should be lingering. Ice should be growing. The long, slow descent into the next ice age should be underway. But it is not. Despite the tilt, despite the wobble, despite the slow pull of the orbit, the summers remain strong. The snow melts. The glaciers retreat. The ice refuses to grow. This has never happened before in the history recorded in Antarctic ice. Never once in hundreds of thousands of years has the planet ignored the alignment of the celestial clock, which means something unprecedented has occurred, something that no ice age cycle had ever encountered, something strong enough to push back against the geometry of the solar system itself. But before we uncover what stopped the next ice age, we must understand what happens when the three gears actually do align, because the celestial cycles do not create ice on their own. They only open the door. The Earth does the rest. For hundreds of thousands of years, the Earth obeyed a quiet command written into the fabric of the solar system. Three slow celestial movements, each operating on its own schedule, each barely noticeable over a human lifetime, drifted through time like gears in an ancient machine. Most of the time, these gears worked against one another. A strong summer here cancelled a weak one there. A circular orbit softened the effect of a low tilt. A wobble in the wrong direction diluted the seasonal contrast. But every so often, rarely and with eerie precision, the gears clicked into place. The orbit stretched. The tilt decreased. The wobble turned northern summer away from the sun. And when that happened, the world changed. The moment of alignment did not arrive with storms or sudden freezes. There were no dramatic signs. No ancient people could have pointed to a specific year or season and declared that the new ice age had begun. It began in silence with the smallest of failures. A patch of snow that should have melted in July did not. A thin layer of frost that should have vanished by August remained into September. A glacier that had been shrinking for centuries stopped shrinking. These tiny events were barely noticeable on the scale of human experience. But the Earth is not governed by human timescales. It moves to rhythms measured in thousands of years. And on that scale, the smallest shift becomes a seismic force. The key to glaciation is always the same. Summer must lose its strength. Winter is never the deciding factor. Winter is predictable. It always brings cold. But summer is the eraser, the cleanser. If summer fails to erase the snow left behind by winter, even by a small margin, the leftover snow becomes the foundation of the coming age. When eccentricity places Earth farthest from the sun during northern summer, the sunlight is weaker. When the tilt is low, that same sunlight strikes at a shallow angle. And when precession aims the northern hemisphere away from the sun, in that weakened summer the result is a perfect storm of cold. Now picture the far north, a landscape that today feels empty, but was once the doorway to planetary transformation. Snow that had melted every year for thousands of years suddenly finds itself living through summer. It lingers on the ground, reflecting sunlight back into space, cooling the air above it. That slight cooling means the next winter begins earlier. The next snowfall lands on top of a layer that never should have survived. This is the moment the cycle takes hold. What follows is not dramatic, not at first. Over centuries, the surviving snow thickens. What was once a thin white crust becomes firn, a dense granular layer. Over more centuries, the firn compacts into ice. The ice begins to flow under its own weight, creeping downhill, carving valleys, pushing its way across the land. Small glaciers merge into larger ones. Larger ones fuse into sheets. The white mirror expands. Every kilometre it gains increases the amount of heat reflected away from Earth. The planet becomes colder not because of the orbit or the tilt or the wobble alone, but because the expanding ice is now reinforcing the cold. The alignment of the celestial gears merely unlocked the door. The growing ice pushes it wide. And this is where the rhythm becomes unstoppable. The feedback loops that govern Earth's climate are like ropes tied to heavy weights. Once they begin to move, they do not stop easily. The planet starts cooling itself. The ocean begins absorbing more carbon dioxide because colder water can hold more gas. The reduction in atmospheric carbon dioxide weakens the greenhouse effect, allowing more heat to escape into space. The air becomes clearer, drier. Snow falls less frequently, but it melts even less often. Landscapes transform. Forests retreat southward. Rivers slow. Grasslands spread across the continents. Animals move with the shifting ecosystems. Humans, if they existed during those periods, would have watched their familiar world dissolve into a harsher, emptier one. At first there is no wall of ice, just a lengthening of winter, a dulling of summer, a sense that each year feels a little colder than the one before. But over thousands of years the change becomes monumental. In Canada, the ice thickens kilometre by kilometre until the weight of it depresses the crust of the continent. In Scandinavia, ice climbs over mountains and fills valleys. In Europe, the Great Plain becomes a frozen desert. In Siberia, the mammoth steppe expands, dry and windswept, illuminated by a pale Arctic sun that barely clears the horizon. The alignment of the celestial gears is rare, but once it occurs, the Earth falls into step with a rhythm more powerful than weather or climate, a rhythm that rewrites coastlines and carves continents. This is the moment recorded again and again in the ice cores, the beginning of each downward slope in the sawtooth pattern, the start of 90,000 years of cold. The melting phase, the sharp upward spike that ends each ice age, is fast. But the freezing phase is slow, relentless, patient. It is the slow inhale of a planet drawing water from the oceans and storing it on land as ice. Each glacial period follows the same script. The alignment of eccentricity, tilt, and precession weakens the summer sun. Snow persists. Ice grows. Feedback loops amplify the cold. The world becomes white. This process has repeated 8 times in the last 800,000 years. 8 long breaths of cold. 8 collapses into warmth. 8 transformations of our continents. And according to the celestial cycles, the 9th cycle should already be underway. The orbit is gradually stretching again. The tilt has been decreasing for thousands of years. Precession is moving northern summer toward the farthest point from the sun. The cosmic gears are almost in alignment. But the snow is not surviving. The ice is not growing. The world is not responding. The cosmic clock is ticking on schedule. But the Earth has fallen out of rhythm for the first time in the history preserved in Antarctic ice. The question that now rises from the data is not what triggers the ice ages. That part of the mystery is solved. The real question is far stranger. What stopped the next one? What force is powerful enough to override the celestial gears that have controlled Earth's climate for 1 million years? To answer that, we must look not to the sky, but to the Earth itself. We must examine the amplifiers that turn small changes into continental transformations and understand how they once obeyed the sky, but now obey something else entirely. When the celestial gears align and northern summers weaken, the Ice Age does not arrive with a dramatic freeze. It arrives quietly, a whisper in the climate system, a subtle softening of sunlight. The orbit nudges the planet farther from the sun. The wobble shifts the seasons. The tilt lowers the height of the summer sky. None of these changes are large enough to freeze the world by themselves. If only the cosmos were involved, Earth would cool slightly and then recover. But the ice ages exist because the Earth itself does not simply receive the celestial signal. It amplifies it. The planet hears a faint whisper from the sky and responds with a transformation powerful enough to bury continents beneath ice. A weakening of summer is only the beginning. What follows next does not come from above, but from the surface and the oceans. Two forces awaken, one bright and reflective, one deep and silent. The first is the mirror made of snow and ice. When summers weaken, even slightly, the snow that falls in winter does not fully melt. A thin layer survives. That thin layer is enough to tip the balance. Snow is brilliantly white, far brighter than forests or ocean water. It reflects sunlight back into space with ruthless efficiency. As more snow survives, more sunlight is turned away. The air above cools. New snow falls earlier, melts later, and spreads across the land. Year after year, the reflective patch expands until it becomes a surface large enough to change the climate around it. What begins as a small remnant of winter becomes a self-perpetuating engine of cold. Snowfields merge into glaciers. Glaciers thicken into domes of ice. Forests retreat. Plains turn pale. The northern continents begin to shine like an enormous mirror, cooling the world far beyond their physical boundaries. At full strength, this mirror becomes a climate system of its own. It no longer waits for winter to expand or for summer to recede. It enforces cold continuously. The orbit may open the door to the ice age, but the mirror pulls the planet inside. Yet ice alone is not enough to drive the world into deep glaciation. A second amplifier awakens as the climate cools, one far more subtle and far more dangerous. This amplifier does not exist on the land. It hides in the ocean. Cold water absorbs carbon dioxide. Warm water releases it. As the mirror spreads and the planet cools, the oceans begin drawing carbon dioxide out of the atmosphere. With every century, they take a little more. As greenhouse gases slowly decline, the planet loses a fraction of the insulation that keeps heat near the surface. Less insulation means more heat escapes into space. The cooling deepens, and the oceans inhale even more carbon dioxide. A quiet feedback loop begins, one far more powerful than the change in sunlight that triggered it. As the ice sheets advance, they grind bedrock into fine mineral dust. Winds carry this dust across the oceans, fertilize in the waters, and feeding microscopic life. These organisms absorb carbon dioxide as they grow, and when they die, they sink, locking carbon away in the deep ocean for thousands of years. The planet begins systematically removing heat from its own atmosphere. The mirror reflects the sun away. The oceans steal the sky. Cold deepens. Ice advances. The gentle push from the orbital cycles becomes a runaway cascade. And once these feedbacks gain momentum, the transformation becomes unstoppable. The climate no longer depends on the tilt or the wobble or the distance to the sun. It is driven by the momentum of the ice and the hunger of the oceans. This is why the descent into an ice age takes 90,000 years, not because the orbital cycles demand it, but because the Earth itself reinforces the cold again and again, creating a new equilibrium. Winds shift, rivers move, shorelines change, the continents sag under the weight of ice, entire ecosystems migrate southward. And once this frozen equilibrium locks into place, small changes in sunlight cannot break it. The world stays that way for tens of thousands of years, until the gears of the cosmic clock align again, but in the opposite direction. When summers strengthen, the mirror weakens. Snow melts earlier, ice thins. The oceans warm and begin releasing carbon dioxide they had stored away. Greenhouse gases rise. The atmosphere regains insulation. And suddenly the same feedbacks that once deepened the cold now amplify the warming. The collapse of an ice age is fast, violent, chaotic. Ice walls crumble. Oceans rise meters within a human lifetime. Floods roar across continents. The planet surges upward in temperature in one of the most dramatic transitions in the natural world. Every termination looks like a vertical spike in the ice core record, a rapid exhale after a long frozen inhale. And according to every rule of the past, our own warm period should be ending now. The tilt is decreasing, the wobble is shifting, the orbit is stretching, the gears are aligning. The mirror and the thief should already be awakening, but they are not. The snow in the far north melts each summer. The oceans are not absorbing carbon dioxide, they are releasing it. The great mirror that once cooled the planet is shrinking instead of growing. And the amplifiers that once responded faithfully to the celestial cycles now remain silent. Something powerful is overriding the ancient logic of the Earth. Something is blocking the return of the cold. Something is breaking the oldest rhythm the planet has ever known. To discover what that something is, we must look not at the sky, but at the scars, the ice ages left behind, scars carved into mountains, buried beneath oceans, and drowned under rising seas. Those vanished landscapes hold the key to the missing cycle. To imagine the Earth during an ice age, you must let go of every familiar map, every coastline you know, every mental picture of continents and seas. The world we live in today is only one version of Earth, one brief arrangement of land and water among countless others that have come and gone. During the long glacial periods, the planet wore a different face. And if you could walk across that ancient landscape, almost nothing would feel recognizable. The ice that formed during each cycle was not the kind that clings to mountaintops today. It was a force, a weight, a presence, a continent-sized mass of frozen water that reshaped the land beneath it. The ice sheets of the past were not passive blankets, they were bulldozers. In North America, the Laurentide ice sheet rose over Canada and the northern United States in a dome of white more than 3 kilometers thick. Picture standing in what is now Chicago. Above you, where skyscrapers and clouds now meet, there would have been only a cliff of ice, glowing faintly in the pale light, silent and immovable. The ice was so heavy that it pressed the crust downward by nearly 1,000 meters, creating a vast depression that still exists today. Hudson Bay is not a natural basin carved by rivers. It is the memory of the weight of ice. Europe had its own frozen giant, the Fennoscandian ice sheet. It blanketed Scandinavia, advanced over the British Isles, and pushed deep into Germany and Russia. What we now call Scandinavia was buried under a dome of ice that would have dwarfed every mountain range in the region. The pressure of that ice smoothed landscapes, ground down mountains, carved valleys, and left behind scars still visible from satellite imagery. Ice sheets do not simply sit in place. They move. Slowly, yes, but with unimaginable power. As they advance, they scrape rock from the continents, grind it into fine powder, and transport it hundreds of kilometers. They reshape drainage systems. They reroute rivers. They carve basins that later become lakes. The Great Lakes of North America are among the youngest major geographic features on Earth. Their shapes were sculpted by the slow grinding of the Laurentide ice sheet. But the story of the Ice Age world is not just a story of ice, it is also a story of absence. When trillions of tons of water become locked in ice sheets, that water must come from somewhere. The oceans are the source. As ice grows, sea levels fall. Not by a few meters, but by more than 100 meters. Enough to expose entire continental shelves. Enough to merge continents that today are separated by wide oceans. This lowered sea level revealed new landscapes that no longer exist. To walk from France to England required nothing more than crossing a broad plain known today as Doggerland. It was a region of rivers, lakes, forests, and grasslands. A thriving ecosystem that once connected Europe to the British Isles. Today it lies beneath the waves of the North Sea, its hills and valleys drowned, its ancient rivers now channels for passing ships. Farther east, the land bridge we now call Beringia connected Siberia to Alaska. But calling it a bridge understates its size. It was a subcontinent, a vast expanse of tundra and grassland stretching for thousands of kilometers. Herds of mammoths, woolly rhinos, bison, and horses roamed across it. Predators followed. And at some point humans did too. For many generations, ancient people lived on Beringia, unaware that they were standing on a temporary world, a world that existed only because the oceans had receded. They hunted, built shelters, raised families, and watched the great herds move across the endless horizon of the mammoth steppe. They likely never imagined that the land beneath their feet would one day vanish beneath the sea, leaving no trace of their presence except what they carried with them into the Americas. The Earth during an ice age was not simply colder, it was larger. Continents extended hundreds of kilometers beyond their current boundaries. Islands were connected to mainlands. Peninsulas stretched further into the ocean. The Mediterranean coastline was transformed. Southeast Asia was linked by land bridges that allowed animals and humans to move between regions now divided by sea. But this world was not static. It transformed steadily over tens of thousands of years. As ice accumulated, the weight on the continents increased. The crust flexed downward. Meanwhile, regions far from the ice sheets rose upward in response. The Earth bent under the load. And when the Ice Age ended, the process reversed. After the rapid warming spikes that ended each glacial period, the melting began. The ice sheets thinned and retreated. The weight lifted. The crust slowly sprang back upward, a process known as isostatic rebound. Even today, thousands of years after the last ice sheets melted, Scandinavia and parts of Canada are still rising by about a centimetre each year. The land is still remembering the weight of the ice. With the melting came floods. Not ordinary floods, but catastrophic ones. As ice dams failed, enormous lakes built up behind them burst open. Walls of water hundreds of meters high swept across the land. One of the most dramatic examples is the scablands of the Pacific Northwest in the United States. Their chaotic channels and deep canyons were carved not by slow erosion, but by megafloods unleashed when glacial ice dams gave way. The landscape bears the scars of these sudden catastrophes. And then the oceans rose. As trillions of tons of meltwater poured back into the sea, coastlines moved inland at astonishing speed. Entire landmasses disappeared beneath rising waters. Doggerland drowned. Beringia vanished. Shorelines reorganized. Islands formed. Peninsulas were cut off. The world contracted again. This transformation was not slow for the people who lived through it. Sea levels rose meters within a human lifetime. Valleys filled with water. Coastlines crept inland like a relentless tide that never stopped. We often imagine the Ice Age as a fixed scene frozen in time. But it was a dynamic era. Continents shuddered under the shifting weight. Ecosystems migrated across thousands of kilometers. Human cultures rose, adapted, and vanished. The world was always moving, and through it all the cosmic cycles continued turning, each one setting up the next transformation. According to those cycles, the next major cooling should already have begun. The world should be slowly entering the first phase of glaciation. Grasslands should be spreading, forests should be retreating. The ice sheets of Greenland and the Canadian Arctic should be growing in quiet, patient layers, but they are shrinking. The map of the Ice Age world is not returning. Instead, something else has happened. Something that has no precedent in the million-year climate record. The trail leads to a single moment in deep time, a shift that rewired the rhythm of the Ice Ages and hints at why the planet may be changing again now. For nearly 2 million years before the world we know today took shape, the Ice Ages followed a different beat. The pattern was steady and predictable. Every 41,000 years the Earth cooled, the ice advanced, and then it receded again. The cycle was shorter, gentler, and more symmetrical than the one that came later. The planet breathed quickly compared to the long, slow rhythm we now associate with the glacial ages. Then, about 1 million years ago, something broke. The 41,000-year cycle faded and was replaced by a new rhythm, one dominated by the long 100,000-year pulses we now see in the ice core records. It was a dramatic shift, one of the most puzzling transitions in Earth's climate history. The world changed gears. The Ice Ages became deeper, longer, and far more brutal. This turning point is known as the mid-pleistocene transition. It is a moment when the rules of the planet's climate system rewrote themselves. And understanding why it happened is essential to understanding why our current warm period should have ended long ago and why it has not. To grasp the mystery, imagine looking at the climate record before the transition. The sawtooth pattern that dominates the last 8 cycles simply does not exist. Instead, the record shows a softer oscillation. The Earth cools, but not as deeply. The ice grows, but not as high. The transitions between warm and cold are smoother. The symmetry between descent and ascent is tighter. The ice sheets then were lighter, more fragile, more easily melted. And then something changed. The ice began to linger. The warm periods shortened. The cold periods deepened. The gentle oscillation sharpened into the jagged peaks we associate with ice ages today. It was as if the planet suddenly decided to hold its breath for longer and exhale more violently. For decades, scientists struggled to explain what could have caused such a fundamental shift. Nothing in the orbital cycles changed. The tilt still oscillated on a 41,000-year schedule. The wobble still traced out its 23,000-year circle. The orbit still stretched and relaxed over 100,000 years. These celestial mechanics are controlled by gravity and mass and inertia, forces too vast to change in such a short geological instant. So if the sky was not responsible, the answer had to be on Earth. The solution emerged from an unexpected place, not from climate models or astronomical theories, but from geology. Specifically, from the behavior of ice. To understand the shift, imagine the Earth's northern continents as they existed 2 million years ago. They were covered in a thick layer of soil and weathered rock called regolith. This layer was loose, crumbly, and unstable. When ice sheets formed on top of it, they did not anchor themselves securely. The ice moved easily across the slippery surface, spreading out thinly but never piling too high. Thin ice sheets respond quickly to changes in sunlight. A small increase in summer warmth melts them. A small decrease allows them to grow. They breathe quickly in and out, following the 41,000-year cycle without resistance. But ice is not just frozen water. It is the most powerful sculpting force on Earth. As it spreads, it grinds. As it grinds, it removes. Over hundreds of thousands of years, the ice sheets scraped away the regolith, stripping the continents down to bare bedrock. Valley by valley, plain by plain, the northern lands were polished clean. And then suddenly there was no more soil. The ice now rested directly on rough, high-friction rock. Everything changed. Thick ice sheets need friction to stand tall. When they sit on soft ground, they slide outward and thin themselves. When they sit on hard rock, they freeze to it. Anchored in place, they no longer spread outward. They grow upward. They become fortresses instead of blankets. Once the regolith was gone, the ice sheets became thicker, colder, and far more resistant to melting. A 41,000-year tilt cycle was no longer enough to wipe them away. Even strong summers could not dissolve them completely. The planet began to skip beats. Ice that should have melted in the middle of a cycle persisted into the next one. It grew thicker during the next cooling phase. It became even harder to melt. After several skipped cycles, the ice sheets reached such size and stability that only the combined force of all three orbital cycles, aligning eccentricity, tilt, and precession, could collapse them. This alignment happens roughly every 100,000 years, and so the rhythm changed, from 41,000-year cycles driven primarily by tilt to 100,000-year cycles in which eccentricity, the weakest of the three orbital forces, became the ultimate trigger for the destruction of massive stubborn ice sheets. The mid-pleistocene transition was not caused by the sky. It was caused by the Earth changing its own sensitivity. The removal of the regolith was a geological reset. The climate system was rewired. The northern continents evolved from soft, thin-skinned landscapes into rigid platforms that allowed ice to reach unprecedented heights. The world entered an era of deeper, more persistent glaciations, the ones recorded in breathtaking detail in Antarctica's icy archive. Once this new rhythm emerged, it dominated. The last 8 cycles follow this pattern almost perfectly, long, slow freezes punctuated by rapid, violent thaws. And according to that rhythm, the next freeze should have already begun. The conditions for cooling are present today. The tilt is decreasing. Precession is shifting the seasons. The orbit is slowly stretching. All the celestial gears that once dictated the timing of ice ages have moved back into their familiar configuration. Yet the ice is not responding. The regolith is gone. The continents are capable of supporting massive ice sheets. The mirror is ready. The ocean is capable of inhaling carbon dioxide. The feedbacks are waiting to activate. But something is holding them back. To understand why the next ice age never arrived, we must examine the end of an ice age, how the great ice sheets collapse, how the oceans surge, how the Earth transitions from frozen to warm in a geological instant, because the violence of that transformation reveals just how strange it is that we are not experiencing it now. Every ice age ends abruptly. For 90,000 years, the world descends into deeper cold, layer after layer of snow turning into ice rising into domes that span continents. Then suddenly, everything reverses. Temperatures spike, ice sheets collapse, oceans surge upward. Landscapes that took millennia to freeze transform in centuries. These endings are known as terminations. They are the sharp upward strokes in the sawtooth pattern of Earth's climate. And they are among the most violent natural events the planet experiences. To understand why the next ice age should already be underway today, we must understand how the last one ended. Because that ending set the stage for everything humans would become and for the mystery we now face. It began with a shift in the celestial gears. About 15,000 years ago, the tilt began to increase, giving northern summers more intensity. Precession rotated Earth's wobble so that summers occurred closer to the sun. Eccentricity, still low but rising, allowed these changes to matter. For the first time in tens of thousands of years, sunlight regained the ability to eat into the edges of the ice. The mirror began to crack. The thief loosened its grip. As the ice sheets warmed, something remarkable happened. Meltwater pooled on their surface in lakes the size of seas. Water is heavy. When enough of it collects on top of an ice sheet, it fractures the ice below. The water plunges downward through vertical shafts known as moulins, reaching the base of the glacier. There, under tremendous pressure, it acts as a lubricant, destabilizing the ice. Large sections of the ice sheet begin to slide. The collapse accelerates. This process does not unfold slowly. Once started, it cascades. Massive chunks of ice break off and surge toward the ocean. These are Heinrich events, named for the scientist who identified them. Armadas of drifting icebergs spread across the North Atlantic, freshening the surface waters and disrupting ocean currents. Meanwhile, on land, the melting continues. Entire lakes held back by ice dams burst without warning. Walls of water hundreds of meters high tear across the landscape. One of the most dramatic examples is the Missoula floods in what is now the Pacific Northwest of the United States. These floods scoured the land into the chaotic channels of the channeled scablands, leaving behind a scarred landscape that appears almost alien. At the same time, the oceans rise. Not slowly, not gradually, but in bursts known as meltwater pulses. Meltwater Pulse 1A, roughly 14,000 years ago, raised global sea levels by around 20 meters in a few centuries. For people living at the time, the ocean did not creep upward. It surged. Coastlines retreated inland faster than any human community could adapt. Valleys filled with water. Islands disappeared. Entire landmasses drowned. Doggerland, which once connected Britain to Europe, vanished beneath the expanding North Sea. Berinia, the vast subcontinent between Siberia and Alaska, sank beneath the Pacific and Arctic Oceans. The world we know today, with its coastlines, its bays, and its islands, was shaped by this violent release of water. And then suddenly, the chaos ended. By 11,700 years ago, the ice sheets were gone, retreating to their present strongholds in Greenland and Antarctica. Global temperatures stabilized. The storms weakened. The oceans settled. The Earth entered the Holocene. We rarely think about how extraordinary that moment was. For the previous 2 million years, the planet had endured a relentless oscillation between deep freezes and brief periods of warmth. Yet the Holocene was different. It was strangely calm, almost unnaturally steady. The climate flattened into a gentle plateau, with temperatures varying only slightly for thousands of years. This stability changed everything. Humans, who had spent hundreds of thousands of years as nomads, suddenly found themselves in a world where seasons were predictable. Rains fell on schedule, winters came gently, summers were reliable, the sea stayed where it belonged. For the first time in human memory, the land was still. We planted seeds, we built villages, we invented agriculture, we created writing, we formed civilizations. All of human history, all of our achievements, all of our myths and monuments were built during this long summer. A summer that, by all the rules of the past, should have ended by now. Because when scientists compare the Holocene to the previous interglacials, one detail becomes unavoidable. The warmth has lasted too long. Previous warm periods reached a peak and then began a slow decline. Within a few thousand years, cooling resumed. Snow lingered in the far north, ice began to rebuild. The descent into the next glaciation started almost immediately. But the Holocene did not follow this pattern. After reaching its peak warmth roughly 8,000 years ago, the world did begin to cool. Snow lines shifted south. Glaciers in the Alps advanced. Tree lines in Siberia retreated. The first hints of the next ice age appeared. This neoglacial trend continued for thousands of years. Then about 5,000 years ago, the cooling stalled. 3,000 years ago, it reversed. Temperatures began to rise again. Glaciers that had been growing began to recede. The Arctic, which should have been strengthening its hold on winter, began to soften. The northern ice sheets did not advance. They shrank. The planet was refusing to follow the script. The reasons for this reversal were not understood at first. For centuries, scientists believed the climate must simply be fluctuating around a natural baseline. But the more evidence they gathered, the less natural the warming appeared. The cosmic cycles were still turning. The tilt was decreasing. The wobble was shifting. The orbit was stretching. By all orbital measures, Earth should have been entering the early stages of the next ice age, but instead something else was happening, something the planet had not experienced for at least 3 million years. Humans had begun to alter the atmosphere. We first cleared forests, releasing carbon stored in wood and soil. Later, we discovered how to mine the carbon buried in coal and oil, the remnants of ancient worlds. And then, in a geological instant, we began burning those stores on a massive scale. The atmosphere thickened with carbon dioxide. The planet warmed. Summers strengthened. Winters softened. The thief in the ocean slowed its work. The mirror on land lost its power. We did not simply warm the world. We interrupted the cycle. By pushing atmospheric carbon dioxide above 280 parts per million, the threshold required for ice sheets to begin expanding, we prevented the next ice age from starting. We stopped the long summer from ending, but this reprieve does not come without consequences. For the first time in millions of years, the Earth is being forced into a climate state not dictated by the cosmic clock, nor by its own feedback loops, but by the actions of a single species. To understand what this means for the future, and for the eventual return of the ice, we must step back and view the planet as more than a system of cycles. We must see it as something alive. There is a way to understand the Earth that does not depend on equations or models or even ice cores. It is older than science and older than language. It comes from simply watching the planet move through time. From that perspective, the Earth looks less like a machine and more like a living body. It inhales and exhales. It warms and cools. It rests and surges. Its climate changes not randomly but rhythmically. Every ice age is an inhale. Every interglacial period like the one we live in now is an exhale. For almost 3 million years, the Earth breathed this way: ice in, ice out, cold in, warm out. A slow, patient, unavoidable rhythm. And then during the brief flicker of time in which humans appeared, something broke that rhythm. The long exhale, the Holocene. The warm period that should have been ending has been extended far beyond its natural life. The breath should have reversed thousands of years ago. The next inhale should have begun, but it did not. The planet is still exhaling. When scientists first realized this, it seemed impossible. Nothing in the last million years suggested that an interglacial period could be prolonged. Nothing indicated the Earth could override the orbital cycles that had dictated its climate for so long. Yet that is exactly what has happened. To understand why, we must return to the forces that once controlled the ice ages. The celestial gears still turn. The tilt is still decreasing. The wobble is still shifting. The orbit is still stretching. The sky has not changed. The Earth has. And the cause is us. In the last few thousand years of human history, we have released carbon into the atmosphere at a rate unmatched in geological time. Not even the melting of past ice sheets released carbon this quickly. Not even volcanic supereruptions altered the climate this dramatically in such a short span. At just 280 parts per million of carbon dioxide, ice sheets can start growing. Below that number, snow survives summer. Above that number, ice struggles to form. For 800,000 years, carbon dioxide never rose far above that threshold. Only for brief moments during warm periods did it exceed it slightly. It always fell afterward, allowing the cycle to continue. Then came us. By clearing forests, domesticating landscapes, burning wood, mining coal, extracting oil, and releasing ancient carbon into the sky, humanity pushed the atmosphere past a point the Earth had not experienced in millions of years. Carbon dioxide climbed past 300 parts per million, then past 350, then past 400, and today it sits at over 420, far above the growth threshold for ice, far above the stability line for the natural cycle, far into a climate state unknown to the world that shaped us. The result is simple and profound. We stop the next ice age. Not intentionally, not with a plan or an understanding of what we were doing. It happened as a side effect of our inventions, our hunger for energy, our expansion across the world. But whether by accident or design, the effect is the same. The planet's long summer did not end, and that changes everything. It means that for the first time in Earth's recent history, the future climate will not be determined by the orbit or by the tilt or by the wobble. It will be determined by the choices of a single species living on its surface. A species that evolved during cold but built its world during warmth. That warmth gave us stability. It gave us agriculture. It gave us rivers that stayed in their banks and coastlines that held their shape and seasons that arrived when we expected them. It gave us time. Time to learn, to build, to grow, to imagine. But it also gave us something else. Responsibility. If Earth is a living body, then we have given it a fever. A fever spreads warmth into every part of the system. It raises temperatures not evenly, but disruptively. It accelerates some processes and weakens others. It changes weather patterns, ocean currents, and the chemistry of the atmosphere. Like any fever, it is a sign of imbalance. The Ice Age cycle has been paused, but not erased. The orbital mechanics still operate. The planet still tilts, wobbles, and drifts along its elongated path. Those signals still push softly toward cooling, but the atmosphere no longer listens. The greenhouse gases we have added drown out the whispers of the cosmic clock. Eventually that carbon will diminish. Eventually the oceans will absorb it. Eventually the land will store it. Eventually the air will clear. But eventually is a long time. When that day comes, whether in tens of thousands of years or hundreds of thousands, the mirror will regain its power. The thief will awaken. The snow that melts today will begin to survive, and the long inhale will return. The Ice Age cycle will resume. Humanity has delayed it, but we have not destroyed it. We live in a unique moment at the top of the warm spike in a climate pattern that has shaped the world for millions of years. A moment when the Earth should be cooling, but is warming instead. A moment when the past is no longer a guide to the future. A moment when we stand between two worlds, a frozen one behind us and an unknown one ahead. This is the part of the story with no precedent. No ice core shows a world like ours. No past cycle offers a map for what comes next. No ancient record tells us how long the pause will last. We extended the long summer. We changed the breath of the planet. We shifted the future. But we also awakened a truth the Ice Ages had hidden. The Earth is not fragile. It is dynamic. It is powerful. It is ancient. And it responds to every force that shapes it. Cosmic forces, geological forces, biological forces, and now human forces. The story of the Ice Ages is not just the story of cycles and climate and ice. It is the story of how a planet evolves and adapts, how it inhales and exhales, how it listens and responds. And now that we have interrupted its breath, the question that rises is no longer why Ice Ages return every 100,000 years. The question is what Earth becomes next, and what we choose to become with it. And if you've journeyed with me to the end of this long breath of the Earth, feel free to leave a like, share this story with someone who would appreciate it, and subscribe so you do not miss the next chapter. As we move into a new year, I want to wish you a quiet moment of peace wherever you are. May tonight's story carry you into a deep, gentle sleep. Good night, and thank you for being here.